paper is called The Visit in the Society of Mind, Convolutional Neural Networks via Multi-Agent Systems. To give you the bottom line on top, it's about finding a new architecture for neural networks, still within the paradigm of artificial intelligence. An introduction. So the main objectives of my paper was to implement a convolutional neural network as a multi-agent system, interpret a distributed multi-agent system as a concurrent actor system, discuss the relationship between object-oriented and multi-agent paradigms, create a supervised classification system, try to improve model performance through parallelism, and determine constraints on concurrency with reference to implementing such a model. The agenda for this presentation, I'll take you through some background. So we'll start with AI programming, I'll define agents and actors, and then I'll speak about machine learning and neural networks as a technique. So that was kind of the background, gives you kind of the thought process for why I wanted to use the architecture that I did. Then I'll speak about my model. My model is called Marvin. I'll tell you about the implementation and the architecture, and then I'll share some of the results with you, and then I'll discuss future work. Some background. So the Society of Mind. Marvin Minsky, this is Marvin Minsky, was the pioneer of artificial intelligence. He wrote the Society of Mind, which is a collection of essays exploring how the mind works. One of his topics was how intelligence can emerge from smaller non-intelligent entities. AI software engineering. So this is a Venn diagram showing the relationship between artificial intelligence, machine learning, and deep learning. So artificial intelligence is creating a system that shows intelligence, and machine learning is one of the ways that you can achieve this. And then deep learning is a type of machine learning. Some differences between AI programming as a paradigm versus normal software engineering. So in software engineering, you're required to write a program and then you'll debug it to get rid of any errors or bugs that you have. AI as a paradigm requires you to implement a model and then you retrain the model to improve its accuracy. And how you determine that accuracy is through an objective function that you define for the model. Multi-agent systems. So agents are computer programs that execute in an environment. You have four basic types of agents: a simple reflex agent, a model-based reflex agent, model-based utility-based agent, and a model-based goal-based agent. And then all of these act in some environment where they get input and give feedback back. And the structure of these elements or these agents are determined by the components that they implement. And then to create a multi-agent system, these agents will work together through cooperation, coordination, and communication. A learning agent. So a learning agent is created by transforming the simpler agents into something better that can learn from its environment. So it has the ability to learn from data, and it has a state which it manages, so it keeps information about what it's learning about the environment. Encapsulation model. So usually what you do to implement an agent is you would use object orientation. An object is something that can encapsulate state, and then it has methods which can update that state. But the methods are only, they need to be explicitly invoked to be able to change or to implement the method on the state. This here is an example of a single-threaded environment. So these methods for these objects will be called, and it's happening in a synchronous order. Now, if you wanted to turn this into a multi-threaded environment, to do that within normal object orientation is very difficult, because now you have to manage the threads, you have to understand parallel programming, and it becomes a far more complex problem. So therefore we look at the actor model. So the actor model is a framework for concurrency in an object-oriented way. Actors are able to communicate with each other via message passing, and they can also send messages asynchronously, and they seem to act autonomously because they have the ability to decide whether they want to respond to a message and how they want to respond. An actor system then, like the multi-agent system, is grouping all these actors together and making them work together. A means of doing that is using something like the actor toolkit. Actors create other actors, so they form a hierarchy of actors. This creates a supervision strategy, which makes it a more fault-tolerant system. And in this way, you can take a big, difficult problem, break it up into smaller problems, and then delegate work to workers, and then they'll all feed back to the master to come up with a solution. Some very basic background on neural networks. So this is a simple feed-forward neural network. They are very loosely inspired by the brain, but the actual clever stuff is based on mathematical and probabilistic principles. A basic neural network has 3 layers: input layer, hidden layer, and output layer. And when it's fully connected, all the nodes from the input layer are connected to all the nodes in the hidden layer. And then each node has an activation function which determines a firing strength. So that kind of gives importance to data coming into the node and then determining the output. Now, a convolutional neural network is a special type of neural network, which is a locally connected neural network. That means that if you look at a hidden layer, it's only a node in the hidden layer is only connected to a contiguous block of input from the input layer. It's a very popular model for image processing. So features are learned by the model. So you can take an image and learn features like shading and edges and stuff like that. And also you can have multiple convolution and pooling layers, and so create like a deep learning network if you want to. The first operation in the convolutional layer is a convolutional operation. Convolving means to slide a filter over the image. So the model has weight parameters, which are called feature detectors, and then they will be multiplied with a small patch from the image and to calculate a new value, and then you'll slide this patch slowly over the image until you've calculated a new matrix from that image. The function, so this indicates an element-wise multiplication function. The next layer is the pooling layer. The pooling operation reduces the output from the convolutional layer. So if you had to take the output straight from the convolutional layer, you'd have these huge matrices and you'd have to do a lot of matrix multiplication, where the pooling layer tries to turn that convolutional layer into summary statistics, and it gives you less output. Examples of aggregation statistics used is max pooling or mean pooling. So max pooling would basically look at a patch and take the maximum value out of that patch. Mean pooling would look at a patch and take the mean of that patch. Model implementation. So my model is called Marvin. It stands for multi-agent recursive intelligent network. Materials and methods. The Marvin actors were implemented with Scala and a message protocol using the actor toolkit. This is a class diagram of the hierarchy. So you have a main actor which creates a master. Master coordinates the data shard actors, and then it creates network actors and gradient shards. So this indicates that you can have multiple of a certain type of actor. This is a sequence diagram. You can't really see anything, so I put this one in here. So that's just an example of the message protocol defined for one of the actors. So the master actor would send a start mini batch to the data shot actor, and then once the data shot actor is finished, it would send a done mini batch back. The architecture is based on the downpour SQD function. It's a stochastic gradient descent algorithm developed for a model called disbelief. So the basic idea is to take the data set, break it up into data shards. Each data shard will communicate with a model replica, and then there's a central parameter server. So what I added was the gradient parameter so that you could parallelize the data shard operation. So the one place, so why I added that was because the single parameter shard was creating a bottleneck. Every time a network finished computing, it had to communicate to a single place, where the parameter gradient shard split up the problem, and then each one could happen in parallel. Results. So I used this model to create a basic image classification system. The MNIST database of handwritten digits is a very popular one for showing that an image classification system works. It's a database of handwritten images where the images are stored in matrices of their RGB values. Some performance measures. So if you evaluate the cost function, so that is the cost obtained from the objective function, it increased from about the 6th mini batch, and then it started to decrease, and about at the 20th mini batch it started to flatten out. This is the confusion matrix, so we got about 94% accuracy, which is very good for this data set. This graph over here shows the true labels, and this is the predicted label. So here 96% was correctly predicted. And then I did some telemetry on the actors. So I looked at a non-parallelized version where you just had one network. So for each data shard, it would have to iterate over the network, computing the data in the data shard. So as you increase the number of data shards, the time increased. But then when you looked at the parallel version, so that means you have a network for each example in the batch. The time decreased as you increase the number of data shards. Feature work. So some enhancements I'd like to do is, so I still worked on a single computer. One of the reasons why I wanted to do this was because CPUs are great and fast, but they're expensive. So how can you do it if you don't have a CPU? A GPU. So I did this on a single computer, and I'd still like to see what it would be to create a cluster using Akka and try and separate it over compute nodes. I'd also like to use it for sequence-to-sequence learning for natural language processing, because convolutional neural networks don't have to just be used for images. And then looking at some other implementations of algorithms like artificial neural networks, self-organizing maps, and symmetries. Thank you.
Thank you for 5 minutes.